Good. Rise and shine, Tucson. I am Aaron Bugaj, the research specialist here at Biosphere 2, and I am coming to you live today from the Landscape Evolution Observatory. This landscape that's below me is an artificial landscape that the University of Arizona studies under glass. And what this landscape resembles is a watershed. It's a catchment basin for rainfall. Now, if you look out into the background of the Catalina Mountains, or any mountains from wherever you are, you'll notice that there are patterns in the landscape. And some of these patterns resemble a convergence zone that you can find below me. Now, that watershed collects rainwater, where the rainwater then funnels underground into rivers and groundwater aquifers at lower elevations. So some of our scientists at the University of Arizona have been studying these watersheds at different elevations for the last 15 to 30 years. And what they found was that while these watersheds are similar in shape, they're different in function. So a watershed at the top of a mountain at, say, 9,000 feet might act quite differently than a watershed at 2,000 feet. This was very interesting to us because when we look at global landscapes and how those landscapes provide drinking water for humans, we want to understand how water transports through those landscapes differently at different elevations, in the presence of different vegetation and soil types. So with that knowledge and with the questions that we had, we developed this project, the Landscape Evolution Observatory, that is an artificial landscape that allows us to compare our field sites with a controllable, large-scale experiment indoors. So to my left and right, along the sides of this landscape, are sprinkler head formations. And we can pump about 20,000 gallons of rainfall out of these sprinkler heads to create a monsoon-like rain. We can create a light sprinkle and quantify rainfall, and then track those water bodies as the rainfall lands on the surface, percolates into the ground, and then travels through the subsurface downslope. Why is that important? So, as scientists, we're interested in things like water quality, the age of our water as it moves through the landscape, and maybe restores our drinking water supplies that we pump from deep in the subsurface of the soil under our cities and towns. And one of the questions we want to know is, how does water chemistry change with contact time of different landscapes? So if I'm making a cup of tea in the morning and I start with a cup of hot water and I add a tea bag into that cup, the water chemistry is going to change based on the amount of contact time that I have with that bag of tea. And taking that analogy, the water chemistry of our rainwater is going to change with the contact time that it has with the subsurface and the soil. So say if we had rainfall that was going directly into our drinking water supply, but it had to travel through a landscape that had contaminants like mine tailings or oil spills, if we know what the contact time and the transit time of that water body is before it reaches our drinking water supply, then we can have an idea of what the water chemistry is, what kinds of contaminants are in our water, and what do we need to do to get those contaminants out. Beyond that, the material that we're studying is a parent basalt material. Basalt is volcanic in nature. We mined this soil from northern Arizona, and what's interesting about basalt as opposed to other parent materials like granite and gneiss is that basalt weathers quite quickly. And in that weathering process, when you have rainfall and water interacting with the minerals in this soil, you get the output of nutrients, which basically enacts a landscape chemistry change, or an evolution as we call it. So we start with this parent material of basalt, and we rain heavily for days or months at a time, and the soil is changing beneath our feet. In order to track those changes, we, upon building this experiment, planted thousands of sensors below the soil. So from 80 centimeters deep to just 5 centimeters deep, just below the soil surface, we've got thousands of sensors that tell things like energy flux or heat exchange with this kind of heat flux plate. We're measuring soil moisture with this soil moisture probe. Additionally, we have things like gas sampling and water sampling probes that physically pull water and gas out of the soil. Now, if these sensors are embedded in the subsurface at different XYZ coordinates, what we've essentially created is a grid of sensors that can tell us how water, entire bodies of water, move three-dimensionally through the subsurface. So imagine if we were raining different colors of water. So I'd start with a water that I dyed red. So I might rain red water on our landscape for 5 days. And then on the 6th day, I might rain blue water. And then on the 7th day, maybe I rain red water again. So instead of using dye, we use isotope-enriched water as our tracer label. When we rain a tracer on the landscape, we can actually track that body of water that's identifiable at a molecule scale through the landscape. That allows us to see how old the water is and get exact data on the transit time distribution of water when it moves from our sprinklers into our soil, when it exits the slope. Some of that water might actually evaporate off of the soil surface back into the atmosphere, and we have instruments that track that too. So we're tracking water through liquid and gas phase. In addition to water, we track carbon on our landscapes, CO2. So just in front of me, you can see this instrumental mast that we have outfitted with a variety of sensors. Starting on your right, we have these black wind anemometers. In the middle, we have syringes that are pulling physical gas samples into a CO2 analyzer. So right now, this sensor is probably catching the CO2 that's coming out of my breath as I talk to you. In terms of CO2, we're interested in tracking changes as microbial respiration pumps CO2 out of the soil and into the atmosphere. And when we add plants, we'll be able to track photosynthesis as we pull CO2 out of the atmosphere and into the soil in a sequestration process. I could talk about LEO all day, and you can actually join me for an all-day tour Saturday the 17th that focuses strictly on the LEO project. Again, my name is Aaron Bugaj, and I'm a research specialist here at Biosphere 2. I focus on this landscape hydrology project. We call it the Landscape Evolution Observatory. If you want to find out more about LEO, you can follow the link below. And if you want more info about my Saturday the 17th tour, you can as well follow the link below to get some info on that. I'd love for you to join me. I have hours of information and things to teach you on these processes that we're studying, and I appreciate your time in joining me this morning at the Biosphere. Take care and have a great day.